Okay, now I want to apply the formula for a regular polygon to some specific examples. And first thing I want to go through is example number 5. You have a regular pentagon, like we kind of just talked about. The radius is 4 inches and the side length is 3 inches. So I'm going to just sketch it out. Here's my regular pentagon. Again, all the sides are congruent. We just figured out that each interior angle is 108 degrees. Just as a quick review, that comes from n minus 2 times 180 and then divided by n. In this case, n is 5 because there's 5 sides. But each interior angle is 108 degrees. But you have a regular pentagon. The radius is 4 inches. So when I draw that, it's from the center to a vertex. So that length is, not 5 inches. It's actually 4 inches. And then each side length is 3 inches. So on part A, we want to find the apothem of the pentagon. So the apothem, remember, goes from the center perpendicular to one of the sides. What's also going to be true, because you have another triangle like this. This triangle right here is going to be congruent to all 5 of the other triangles if you draw a radius. Even though I didn't inscribe this in a circle from here to here, the center to a vertex, that would be a radius. But I have 5 congruent triangles, or this right triangle right here in this regular pentagon, there's 10 congruent right triangles like this. I could have drawn this right triangle, but you just need one in order to find the length of the apothem. But to find the apothem, I'm using this right triangle right here. Okay, one of the sides, or in this case, it's the hypotenuse of the right triangle, is 4 units in length. This leg right here is not 3 inches in length. The whole side of the pentagon is 3 inches. So what should happen is the apothem that I drew cuts one of the sides into 2 congruent parts. So if I redraw just the right triangle right here, that's the radius of the pentagon. It's actually the hypotenuse of the right triangle. That's 4 inches in length. This side length right here is the same as this leg right here. Again, it's not 3 inches, but half of that. So that's 1.5 inches. And then in order to calculate the apothem, here's the apothem. It's the other leg of the right triangle. So we could use the Pythagorean Theorem in order to calculate the length. You could also use trigonometry, because if you take a look, this angle is 108 degrees. This angle right here, if you can see where I'm drawing, is 108 degrees. You could take half of that in order to find this angle, which is this angle right here. It might be easier to take a look at this right triangle. So this angle is 54 degrees. But since I have 2 sides of the right triangle, I could use the Pythagorean Theorem as well. So to find the length of the apothem, we could do 1.5 squared, that's one of the legs, plus a squared is equal to 4 squared. And then just do the math from there. So 1.5 squared, that's 2.25, plus a squared is equal to 4 squared, which is 16. And then we could subtract 2.25 from each side, so 16 minus 2.25 is going to give you 13.75. That's a squared. Sorry, I'm running out of room here. And then you take the square root to find the length of the apothem. So the square root of 13.75 should get about 3.7. Once we have the apothem, now in order to calculate the area, if you remember the formula for a regular polygon, 1/2 the perimeter times the apothem. So it's 1/2. If each side length is 3, there's 5 sides, they're all congruent, then the perimeter is 5 times 3, the number of sides multiplied by side length, or 15. And then the apothem we found to be about 3.7 if we're rounding that to the nearest tenth. So I could just multiply 1/2 or 0.5 times 15. Again, this is 5 times 3, so that's 15. And then multiply that by 3.7. We get about 27.8. In this case, it would be square inches for the area of the regular pentagon. For the next example, we have a regular hexagon. So a regular hexagon would have 6 sides. All the sides would be congruent. And the apothem is 10 units in length. And that's all that we're given. So A here is 10 units in length. We want to first find the radius of the hexagon. So we can create a right triangle here. In order to find the radius, which is going to be right here, which is the hypotenuse of the right triangle. So this is the right angle here. We have the apothem is 10 units in length. We're going to have to find some angle measures. So in order to find the angle measures, you can do one of two things. You can find the measure of this angle right here. Another way that you can find the measure of an angle is, let me redraw this hexagon a little bit bigger. But here's the center. Again, we're trying to find this length right here, the radius. This is the apothem. It has to go from the center, perpendicular to one of the sides. It's actually always going to bisect one of the sides if it's a regular polygon. But the apothem here is 10 units in length. But here's what we can do as well. We could find the measure of a central angle. So like we were going over with pentagons, there's going to be congruent triangles. For a pentagon, there's going to be 5 congruent triangles. In this hexagon, this triangle right here is congruent to all 6 of these other regular triangles or equilateral triangles. In order to calculate angles, we could take 360 and then in this case divide it by 6. So the measure of each of these central angles right here, 360 divided by 6 since they're all congruent. Or in other words, 60 degrees. So for this triangle right here, I'm just going to redraw it. This is 60 degrees. But here's what we're more concerned about. This right triangle right here. So we're actually just taking half of that. Sorry, I'm making a lot of drawings here, but I want you to just be able to see what we're doing. This right here is half of the 60-degree angle. So this angle would be 30 degrees. This is 90. We actually have a 30, 60, 90 triangle. The apothem right here, which is this length right here, is 10 units. And we want to find the length of the radius. So to find the length of the radius, you could use a 30, 60, 90 triangle. Here's what I'm going to do. I'm going to use trigonometry. So we have to remember back to SOHCAHTOA. I'm going to use the 60-degree angle. You could use a 30-degree angle as well if you wanted to, but I'm going to use a 60-degree angle. 10 is the leg opposite the 60-degree angle. The radius is which is what we're trying to find is the hypotenuse. So if we have the leg opposite and the hypotenuse, we have to use sine. So the sine of 60 degrees, that's equal to, again, this is S-O-H of SOHCAHTOA, the leg opposite over the hypotenuse. And then if you remember how to solve when the variables in the denominator, we first have to multiply each side by r. So it's r times the sine of 60 degrees is equal to 10. And then divide each side by the sine of 60 degrees. So on my calculator, it's in degree mode, first of all. I'm going to take 10 and then divide that by the sine of 60 degrees. So then the radius, once I do that, if I round it to the nearest tenth, is about 11.5. In order to find the area, here's what we do from there. So if you can kind of make sense of my diagram right here, I'm going to draw it in this regular hexagon. We're trying to find on part B the area of the regular hexagon. Here's what we do have. The apothem, that was given. That's 10 units. We found the radius. That was not given. That's 11.5 units. But this is just practice to find the radius if you're given the apothem, because what we really need to find is a side length. So in order to find a side length, we have 2 sides of the right triangle. Okay, we can find the third side. I'm going to call this X right here in the right triangle. X on my hexagon is right here. It's half a side length. So in order to find X, we could use the Pythagorean Theorem. You could use trigonometry as well. If I use the Pythagorean Theorem, the side length is 11.5. This is 10. So we could do X squared plus 10 squared is equal to 11.5 squared. Do 11.5 squared. That's what I'm doing on my calculator right now. Subtract 10 squared. And then don't forget, that's X squared. So you need to take the square root. So X is about, if we take the square root of everything that I just did, it's going to be about 5.7. That's X right here. If you can see what I have in the diagram, in order to find a side length, that's not X. X is half a side length. So I got X is about 5.7. So I'm going to multiply that by 2. Then each side length is about 11.4. So we could use that in order to help us calculate the area. Sorry, it's all messy right here, but there's a lot going on. Area is 1/2 the perimeter. Again, each side length is 11.4. So I'm going to multiply that by the number of sides, in this case 6, because it's a hexagon. And then the apothem that was given, 10. So now we can multiply all these numbers together. 1/2 or 0.5 times 11.4. Multiply that by 6, and then multiply that by 10 finally. So 0.5 times 11.4 times 6, and then multiply that by 10 would give you the area is about 342, in this case, square units is the area of the regular hexagon.